Okay, thank you to the organizing committee for the invitation to come here. Today I'm going to be talking about an airborne electromagnetic survey that we flew in the McMurdo Dry Valleys in Antarctica. And this is very much an ongoing research project. We just completed flying about 2 weeks worth of surveys last October. But I thought it could be interesting today to share a bit of a project overview, talk about some of the research questions we're investigating, and share with you some of the insights that we're pulling from this data. But before we jump into the project, let me take a moment to acknowledge my co-authors. It's a very large research project, and I'm just one small part of it. But we have team members at Aarhus University, which is where I'm based with Esben Auken in the Hydrogeophysics group. We're, I guess you could say, the EM guys in the project. We have glaciologists at the University of California at Santa Cruz, in particular Slavik Tulicek, who's a PI on the project. We have microbiologists and Jill McCookie at Tennessee, limnologists that study lakes and climate change in the dry valleys, and Peter Doran at LSU, and Hillary Dugan at Wisconsin. And finally, we have an ecologist in Ross, Virginia at Dartmouth College. So it's a very diverse research team that brings a lot of different perspectives and allows us to use the EM data to study a lot of very interesting applications. But first, let's get ourselves oriented. So the dry valleys are located in Antarctica near the McMurdo Sound and the Ross Sea. So as reference, this is the part of Antarctica where Amundsen and Scott launched their South Pole expeditions from about 100 years ago. A couple more reference points. I put Melbourne here and Christchurch. And when we were flying these surveys in Antarctica, the way that you get into McMurdo is you catch a C-17 from Christchurch, and it's about a 5-hour flight straight south to McMurdo. If we zoom into the McMurdo area here, McMurdo is shown by this red star here. So when you're flying into McMurdo, you're actually landing on an airfield that's on the ice shelf. So you land that C-17 aircraft on an ice runway. And that's actually what we were seeing in the title slide, is just the airplane sitting there on the ice runway. And when you get out of the airplane, they put you in a school bus that belongs in Mad Max, and they drive you to McMurdo Station. And so McMurdo Station itself is not actually on Antarctica proper. It's on neighboring Ross Island here. And if there's any volcanologists here, you might be interested to know that Ross Island is home to Mount Erebus, which is one of only 5 volcanoes in the world with an active lava lake. But when we were down there, we flew some of the surveys out of McMurdo Station itself, but we also flew surveys out of another manned base called Marble Point, which is more or less a glorified gas station. It's just a refueling stop for the helicopters as they hop from McMurdo to various destinations throughout the dry valleys. But it was a big advantage for us to be able to launch and host the system at Marble Point because it really let us reach much deeper corners of the dry valleys. So the dry valleys consist of this network of valleys that you see here. So kind of these valley systems running perpendicular to the coastline here. They're described as hyper-arid polar deserts, so they get very little precipitation per year, less than about 50 millimeters on average. They're very cold. Mean annual temperatures are down around minus 20 degrees Celsius. In the summers, that's rising to a balmy minus 10 degrees Celsius or so. And the reason that people are so interested in studying the dry valleys is that they represent an opportunity for researchers to get up close and personal with systems and processes that are playing key roles in driving global climate. So it lets researchers study systems that are particularly sensitive to changes in climate, systems that can act as early warning signs, if you will. It's also extremely valuable in terms of understanding the state of Antarctica under past climate scenarios, which is, of course, important to be able to predict the behavior of Antarctica under future climate scenarios. There's also a group of people that are interested in the dry valleys because they represent a terrestrial analog for Martian conditions. So the extreme dry, extreme cold conditions you encounter in the dry valleys are representative of what you might encounter on parts of the Martian surface. But to give you a little bit better idea of what the dry valleys actually look like, let's zoom in to the ground level here. So we're going to look at a picture that's taken in the Taylor Valley, which is historically the most studied of the dry valleys. And then we'll look at another picture taken in the neighboring Wright Valley to the north here. So in this picture on the left, we're standing on Lake Frixell, and we're looking into the Taylor Valley here. You can see the Canada Glacier off in the distance. And so it's certainly not the case that the dry valleys are devoid of liquid water. They're home to a number of lakes and ponds. It's just that these lakes are generally completely covered by ice throughout the year. On this right image here, we're looking down the Wright Valley, and you can really begin to appreciate how little snow and ice there is in these dry valleys. Although at times it can be somewhat misleading because in the foreground in this image here, we actually have what's called a rock glacier. So this is a glacier that's had its top covered up by sediments that have either fallen off of the valley walls or been blown in by strong winds. And so what we're interested in studying in this project is regional groundwater systems throughout the dry valleys. So some of our research questions include trying to better understand the conditions at the base of the glacier, so that bedrock-glacier interface. We're trying to understand if there are connections between these different surface water bodies throughout the dry valleys, and trying to delineate boundaries like permafrost, bedrocks, these kinds of things. And to answer these questions, we turn to an Airborne EM tool, because Airborne EM is a tool that's particularly well suited to imaging these types of targets, because we expect these targets to coincide with very large contrasts in electrical resistivity. And so Airborne EM is very good at imaging those types of contrasts. The particular system that we flew with was the SkyTem 312 system, which is a dual moment system balancing high resolution in the near surface with large penetration depths. Very briefly, the way that the system works is that this large frame, about 20 meters in dimension, is picked up and flown underneath the helicopter, and data is collected as the helicopter is flying. The way that the measurement works is that you're pulsing a very strong current in a transmit coil that's strung around the exterior of this frame, and you're trying to turn off that current as fast as possible. Because when you're ramping down that current, what's happening is that you're generating time-varying magnetic fields in the subsurface that create eddy currents. And these eddy currents in turn generate their own secondary magnetic fields, the strength and time dependence of which can be measured by a receive coil that in this case is mounted at the rear of the frame. And then what you can do is that you can invert those measured secondary fields to produce images of what the electrical resistivity structure is in the subsurface. And then you can take advantage of the fact that generally when you're viewing images of the electrical resistivity structures, they tend to coincide quite strongly with structures in the hydrogeology. So in the dry valley context, when we're seeing very resistive subsurfaces, they tend to be interpreted as ice and bedrocks. And when we see low resistivity subsurfaces, we tend to interpret them as brine-saturated sediments, bulk waters, and permafrosts. A little bit more specifics about the survey that we flew. So we spent about 2 months in Antarctica last fall. We got in 21 total flights and surveyed about 3,500 kilometers of flight lines. In this map view over here in black, you're seeing all of the flight lines that were flown. So you can see many of the flights originated out of McMurdo Station itself, with the remainder starting out of this Marble Point station here. And in this image, you can really kind of appreciate where our mindset was when we were planning these flights. Many of these flights, they fly as far up a particular valley as we could get, to a point where when you turned around, you had enough gas to get back to Marble Point. Of course, you build in a buffer, but this is kind of illustrative of what our mindset was. It was trying to regionally scout as much of the dry valleys as possible. In red, we're showing locations where we've actually delivered images of what the electrical resistivity structure is. What that means is that when you move from red to black, and this is something that we've had to be very careful in communicating to partners, it doesn't mean that data becomes particularly poor quality at this point or that the system is misbehaving. It just means that you're moving into a region where the subsurface is so resistive that it can't produce a signal that exceeds the input noise levels of the system. So it doesn't mean that you can't use that data for anything. It just kind of limits your ability to actually image what the subsurface properties are. But you can still say with confidence that there's at least an absence of conductors down to our penetration depth, or more or less that it's very resistive anywhere we just have these black lines here. But this survey does not exist in a vacuum. It's actually a follow-up survey to one that was flown in 2011, so another SkyTem survey. In blue here, we're seeing the flight lines from that earlier survey. But they had more focused targets throughout the Taylor Valley here, even surveying at the foot of Mount Erebus. And in the interim between the two airborne surveys, there was a number of ground-based TEM measurements that were done as well. They were done in order to use very large moment transmitters and long stacking times to try and increase penetration depths. But today I think we'll focus on just the two airborne data sets, given that it's an airborne conference. But I thought it could be most interesting if we talked about a few of the high-profile targets that we were trying to image. So we'll talk about a feature known as Blood Falls. We'll talk about Juan Pond, which is the second saltiest body of water on planet Earth. And we'll talk about Lake Vanda, which is the largest lake in the dry valleys. But first, let's turn our attention to this Blood Falls feature, which is a naturally occurring feature that gets its name from this blood-like orangey-red stain that exists at the foot of the TaylorGlacier. And the origin of this stain is from brines that are discharged by the glacier. And during these discharge events, the brines actually come out clear. It's only after a couple of days do they turn this orangey-brown color. And the reason for that is that the brines are rich in reduced ferrous ions, because the source of these brines is home to an active community of iron-breathing microbes. So just as many organisms prefer to breathe oxygen, in the absence of oxygen, you can breathe or get your energy from other compounds. So for example, you can breathe hydrogen sulfide as one of them. There's a number of these different energy cycles. But all the way at the bottom of these energy cycles, you have the iron cycles. So when everything else has been reduced, you're left with these iron-breathing microbes. And there's a lot of interest in better understanding blood falls because it represents an opportunity to better understand life at an extrema, in particular the very salty, very cold, no oxygen extrema. Because these are conditions that you might encounter under, say, the polar ice caps on Mars or on Europa. And there's been a lot of studies done at blood falls, always from the surface, but there was still a lot of uncertainty as to the origin of these brines and the expanse of this iron-breathing microbial community. So one of the targets they had in the 2011 survey was to try and better understand the origin of these discharged brines. Here in this image, we're looking at the flight lines that were flown during 2011. So this is the TaylorGlacier over here. As reference, Blood Falls is sitting right here at the foot of the TaylorGlacier. And what we're going to look at next is a resistivity profile that was produced along this red line. So in this profile, as we move from left to right, we're moving from the TaylorGlacier down the Taylor Valley and ending here in McMurdo Sound. But for now, I want us to focus on the left-hand side of this image. So the way that you can interpret these resistivity profiles is that wherever, or given the particular color at each location in the subsurface, that corresponds to what the local estimate of the electrical resistivity is. So in the TaylorGlacier, where we have ice, we have very resistive values, so it shows up as purple. And then in areas where we have lower resistivities, like in the bulk waters of Lake Bonny, we have lower resistive colors, which are blue. But when they produced this image, what they were very surprised to see was the presence of this expansive low resistivity unit underlying the TaylorGlacier, because it appeared to show a hydraulic connection to Blood Falls. So in 2014, McCookie and others returned to the TaylorGlacier with an ice drill, and they actually drilled through the TaylorGlacier and intercepted this brine, and they sampled the properties of these brines at depth. And they found that the properties of these brines were consistent with those being discharged at the surface of Blood Falls. So a very strong validation that this is in fact the brine reservoir that's sourcing the discharges at Blood Falls. And so this had big implications for their understanding of the system because it suggested that the reservoir sourcing these brines was far more expansive than previously thought, stretching far back beneath the TaylorGlacier. But it also has big implications for the understanding of the TaylorGlacier itself, because the understanding, or the prevailing thought at the time, was that all glaciers throughout the Dry Valley should be cold-based, which means that they should be frozen to that bedrock interface at the bottom. If that were the case, what we should see is purple all the way down to our penetration depth here. But instead, the presence of this brine reservoir, this low resistivity unit, when you combine that with the temperatures that you would expect at the base of the TaylorGlacier, it suggests that these should be unfrozen brine-saturated sediments. So what that means is that instead of being cold-based, the TaylorGlacier is in fact wet-based, which is a very different lower boundary condition and has potentially big impacts on the ice flux rates, the flow of the TaylorGlacier, and that's because a wet-based glacier can slide across that bedrock interface, where a cold-based glacier flows primarily through internal deformation. And so in 2018, we returned to the TaylorGlacier in an attempt to expand coverage of this brine reservoir and try to increase our penetration depths with a larger moment system. But one of the great things you can do when you have such dense 3D coverage is that it allows you to visualize the system in 3D, which is an important tool when you're trying to better build out your conceptual understanding of the system. So what we're looking at in this image here is a 3D voxel representation of the TaylorGlacier. So each voxel's color corresponds to what the local resistivity is. This is shown with a vertical exaggeration with a factor of 5, just as reference. But this big, thick purple unit here, that's the ice in the TaylorGlacier. At the foot of the TaylorGlacier, we have these conductors, which are just the bulk waters in Lake Bonny. Again, the Blood Falls feature would be sitting here right at the foot of the Taylor. But what you can do in an image like this is you can strip off all of the voxels that have very high resistivities, or at least some resistivities exceeding a certain threshold. In this case, we use a threshold of 150 ohm meters, and you can produce an image of only that low resistivity unit at the bottom of the aquifer. So a very powerful visualization of what this lower boundary condition is. It tells us that this brine reservoir is nearly as wide as the full extent of the TaylorGlacier and stretches as far up valley as we have data support. At this point, it's difficult to say whether or not that brine reservoir actually terminates or is just dipping beneath our penetration depths. Both would be consistent with the data more or less. But overall, it's a big change in our understanding of that lower interface on the TaylorGlacier. And from this, the natural next question is, can we expect these subglacial brines to exist at other glaciers throughout the dry valleys? And it's natural to be skeptical of that because The only place where we've imaged these subglacial brines at the time the survey was flown was at the TaylorGlacier. But then again, the TaylorGlacier is only the only glacier with this kind of bizarre superficial expression of this blood falls. So one of the questions going into the 2018 survey was, can we find these subglacial brines throughout other glaciers in the dry valleys? So one example I'll show now. So right now we're sitting in the Taylor Valley, so the Taylor Glacier is right here. We're going to step one valley to the south and talk for a second about the Farrar Valley. The Farrar Valley is different in that the FarrarGlacier encompasses the full valley and is able to punch out all the way into McMurdo Sound. And so again, we're visualizing the FarrarGlacier here in this 3D voxel manner. So again, this thick purple unit, that's the ice in the FarrarGlacier. Interestingly, so there's a thinning that happens here at the foot of the, or at the front of the glacier. In part, that's because we're imaging what's called the glacier tongue. So there's a point that actually takes place around here where the glacier breaks from that bedrock interface and begins floating on the seawater. And so in part, this is thinner because the glacier tongue itself is also thinning, but it's a DOI effect in a way, because as soon as you get through the glacier and hit that sea ice, you quickly lose penetration depth. And so it's kind of, in part, a bit of an illusion that it appears to be extra thinning at the glacier tongue. But of importance was whether or not the FarrarGlacier also had this subglacial brine layer. So we can go through this same exercise and strip off all of these voxels with very high resistivities, exceeding some threshold, and we can isolate the extent of this low resistivity zone underlining the FarrarGlacier. And again, what we see is that this subglacial brine expands the full width of the valley and stretches as far up valley as we have data support. So it seems that the FarrarGlacier, just like the TaylorGlacier, appears to be a wet-based glacier. And we've surveyed many of the other major glaciers throughout the regions, and you find more or less similar features. It's not always as all-encompassing as these two examples seem to show, but in areas you find pockets of brines, some areas you don't find any brines, but it's kind of giving insights that that lower boundary condition throughout the dry valleys is far more heterogeneous than previously thought. Shifting gears, let's now talk about Don Juan Pond, which is the second saltiest body of water on planet Earth. It used to have the distinction of being the saltiest body of water, but it got bumped out of the top spot by a pond they found in Ethiopia about 10 or 15 years ago. But it's still a very interesting number two. Here in this satellite image, you can see the full extent of the pond in its current state. It's about 300 meters long, about 100 meters wide, and at its deepest point, it's about a foot deep. Most of the pond is about 10 centimeters deep or so. This is a rock glacier neighboring the pond here. This is actually the same rock glacier that we saw in an earlier image. But the salinity in the pond is extremely high. It has 33% salinity, which is so high that this pond can remain unfrozen down to temperatures as low as minus 50 degrees Celsius. So this pond effectively just remains unfrozen throughout the entire year. And the salinity in this pond is far too high to only be a consequence of evaporating freshwater meltwaters that are coming from the neighboring rock glacier. So it's thought that there must be some groundwater system of elevated salinity that's recharging this pond from the bottom, and that through evaporation, the pond has been able to concentrate these brines to its current state. Another very interesting feature about Don Juan Pond is that it has an extremely low water activity. So water activity is a number that's useful when you're trying to decide what kind of organisms can live in a particular brine. So the water activity is simply the pressure of brine at a particular temperature divided by the vapor pressure of pure water at that same temperature. So bacteria can live in brines with water activities as low as 0.91. Fungi can live down to water activities of 0.7, and there's never been life observed at water activities below 0.6. And in Don Juan Pond, we have water activities between 0.3 and 0.6. So the pond is effectively devoid of life. And it creates this very interesting scenario where if you move just a couple hundred meters away from the pond, you can find thriving microbial communities living in the soils. You move a couple hundred meters back, and there's a complete absence of life. So it's this very compact system where you have an extreme gradient from no life to life. And so it's kind of this natural little laboratory where you can study life at this very cold, very salty extrema. But our focus in our survey was to try and better understand the groundwater system that's thought to be recharging Don Juan Pond. So in total, we flew 4 lines transecting the pond. Here we're looking at one of the profiles that was produced from a line that flew across the center of the pond along the major axis here. The pond actually sits above this low resistivity zone here. So the subsurface immediately under the pond is very low resistivity, which is what you would expect given the very high salinities in the pond. As you move to greater depths, there seems to be a bit of a gradient towards slightly elevated resistivities. It's difficult to penetrate to great depths underneath the pond given the very conductive overburden. But we see that this low resistivity zone stretches underneath the rock glacier to the left in this image here in a similar manner to what we saw at the Taylor. To the right of the pond, there's a similar feature dipping away from the pond that either terminates not too far from the pond edge or is dipping beneath our penetration depths, perhaps. But in the rightmost of this image, we see that we're just getting into this thick resistive zone here, purple all the way down to our penetration depths. This is one of those scenarios that if we had tried to extend this profile further down the valley, this is those situations where we're dipping beneath the input noise of the system. So further to the right in this profile would just be, we can only say that it's resistive to our penetration depths. So in terms of better understanding this groundwater system, what we can see is that there is in fact groundwater that appears to be recharging the pond. The system stretches underneath the neighboring rock glacier, but it's difficult for us to say anything about the regional expanse of this system, in part because we're limited by depth of penetration underneath the pond, and then this very thick resistive overburden as soon as we get away from the pond. So one of the initial questions we had was whether or not this Don Juan system showed any connections with Lake Vanda further down the valley, but this data unfortunately is unable to confirm that there's any kind of groundwater link between the two. If there is, it's at least at depths greater than our penetration depths. Shifting gears to Lake Vanda, which is this lake here that you can see in this image. It's the largest permanent lake in the dry valleys. It's about 4 or 5 kilometers long and about 2 kilometers wide. And at its greatest depth, it's about 70 or 80 meters deep. It has permanent ice cover, and its primary water loss mechanism is through ablation at the surface, so sublimation at that ice-air interface. The lake in its current form has a very interesting structure. It's segmented into 3 distinct stable zones. Here we're looking at depth profiles showing in blue the electrical conductivity as a function of depth, and in red the temperature as a function of depth. And these profiles are just taken from this Kassendick 2016 paper. This image here is just a rescaled version of this image, so you can actually see the changes in the conductivity. But what's very interesting about this profile is that it shows that this upper layer that they call the upper convective cell, it has a very uniform electrical conductivity and temperature, followed by a short transition zone to a lower convective cell that is also very uniform in terms of electrical conductivity and temperature. But then once you dip down to this diffusion zone, you see this strong gradient both in electrical conductivity and in temperature. And I want to point out the temperature axis here. It goes all the way up to 22 degrees Celsius. So this says that at a lake that's a permanent ice-covered lake in Antarctica, you have a brine layer at its base that's 22 degrees Celsius, which is quite amazing, I think. To explain this type of stratification, it's thought that historically, it's known that Lake Vanda has fluctuated quite a lot in its volume, but it's thought that at its previous low stand, the lake reached a salinity level such that it lost its ice cover. It's thought that it couldn't have achieved such a salinity level by only evaporating freshwater meltwaters that are coming in from the Onyx River. So just like Don Juan Pond, there's thought to be an elevated salinity groundwater system recharging the lake. But at this point, it was being recharged predominantly from this groundwater system, evaporating these brines and concentrating. And at some point, there was a large influx of fresher meltwaters that formed a pool of fresh water on top of that lower brine unit. And at some point, that fresh unit was able to form ice cover over the lake. And once ice cover formed, it effectively stabilized this stratification because it stopped any turbulent wind mixing, more or less. And if you expect this system, or if we expected this system to be dominated by temperature effects, it should be unstable because this warm brine at the base should be lower density and should therefore rise to the surface. But it's actually offset by the concentrations in the brine. So the extreme high concentrations of the calcium chloride brines are able to balance this density contrast and stabilize this kind of vertical structure here. But in our survey, what we were interested in better understanding was some of the plumbing. So what is this groundwater system that's recharging the base of Lake Vanda, and how laterally expansive is it throughout the valley? So here we're looking at a profile that's produced that transects the lake. One of the first things you can see is it's quite a heterogeneous system. So on the right-hand side here, we have very shallow waters, so seen as this low resistivity zone here, underlain by this thick resistive packet. So it doesn't necessarily seem that there's a groundwater recharge system to the northern end of the lake. When we get into the thickest part of the lake here, we can kind of see this stratified nature, even in this smoothened version, which is an irregularization scheme ideally suited to reproduce such a stratified structure. But you can see this more resistive upper layer getting into this lower convective cell where we're seeing a decrease in electrical resistivity, and then a strong gradient as we reach the base of this lake. The lake bottom is actually about at the top of this dark blue layer here. So it's saying that the brine or the sediments at the base of the lake have very low resistivity, perhaps some super concentrated brines from earlier low points of the lake or evidence of some deeper groundwater system recharging the lake. It's difficult to say given only the EM data. But if we move to the tail of the lake here, again, these lower resistivity zones correspond to the water bodies you can see at the surface, and then there appears to be some kind of a connection here. But overall, a quite heterogeneous system. If we move to the lake edge, when we're away from the deep waters here, we quickly are getting into these very thick resistive zones, and then when we're over the lake center here, we're seeing these lower resistivity lake waters underlain by this this reduced resistivity. So perhaps this same groundwater system recharging the pond. But it's difficult to say whether or not this is a system that's perhaps connected to Don Juan Pond or laterally extensive throughout the valley, because as soon as we get away from the lake edges, we get into these very thick resistive overburdens and lose the ability to track this groundwater system. But this is very much an interpretation in flux. It's a very heterogeneous system, and our partners are working with better integrating some of these EM results with the wider data suite that's available at Lake Vanda. But wrapping up, I think this project's a great example of the value that Airborne EM can have, especially in the dry valleys where it's provided really powerful insights to a wide range of different systems. I mean, it's being used to better understand a microbial environment. Very interesting applications of the Airborne EM tool. If you're interested to learn more about the project, there was a great Wall Street Journal article about it that has a really amazing video, and I would recommend all of you to watch the video. It has stunning footage of the system flying in the dry valleys. They actually did a follow flight where they had a second helicopter flying with the system and doing very high quality video. And there's just great videos and photos of the dry valleys as well. Thank you for your attention.